Hello, Algebra 2 students. This last lesson for Chap 8 is on natural logarithms. And basically, it's going to be the same work that we've been doing with regular logarithms or common logarithms. It just has base e. So, quick little definition here. If we have this exponential, y equals e to the x, then could you switch that into the logarithmic inverse here? So that would be log base e of that y gives me that exponent x. And so we just abbreviate natural log, so we don't have to write the log and base e every time. We just do ln for natural log. That's the same thing as saying log base e, just a shortcut for that. And so this would be the equivalent expression. So the first example just has us working through some expressions. Can we use those same properties for logarithms, the power, the quotient, the product properties, given this problem here? So I've got natural logs of 12 and 9 here. We got 2 times the natural log of 12, subtract natural log of 9, and we're asked to make that into one logarithmic expression. So when it's multiplication out here, that's the same thing as 12 squared, and then minus, that's going to be over 9. And then we can simplify this. 12 squared is 144 divided by 9. Final answer gives us natural log of 16. Alright, that's the first one. I'll give you one to try by yourself here. So give this one a go. I'll throw a variable or two in here. So 3 times the natural log of x plus the natural log of y. Go ahead and give that one a try. Alright, so you should have had natural log of x to the third times y. Alright, second one now involves a physics problem about getting a space rocket or a satellite up into orbit. And so they tell us that you have to get to 300 kilometers above the Earth to reach a stable orbit. And they also tell us that we need to get 7.7 kilometers per second for our maximum velocity in order to get up to 300 kilometers. So if you look on page 463, example 2, it goes through the same equation that I'm going to show you here, but just different numbers. So I'll just give you a second example to work with. So it's kind of a scary looking equation. It's maximum volume equals the negative 0.0098 coefficient times t plus c natural log r. And so this is a physical world relationship done with physics problems. And so we have to know what these different parts are. So like I said, v is going to be the maximum velocity of the rocket. And then that capital R, that's actually a ratio. It's the ratio of the rocket when it has fuel in it. So fuel is in it compared to the rocket after all the fuel is burned off. And they're going to give us most of these numbers. And then the t, the time, that's actually how long the booster rocket is going to fire. So that's in seconds. And then c, that is the exhaust velocity. And so they're going to give us all but one of these numbers, or all but one of these variables, numbers for them. So we've got the r given to us as being 22, so the rocket is 22 times heavier when it's got all the fuel in it versus once it's all burned off. The exhaust velocity is 2.3 kilometers per second in this problem, and then the time that the booster rocket is firing is 50 seconds. And the question is this going to be able to reach a stable orbit of 300 kilometers? And so the only number that I'm not given is the maximum velocity. So the t, the c, and the r I have values for, so it becomes a calculator exercise. So we got negative 0.0098 times the 50 seconds that the exhaust velocity or booster rocket is going to go, and then now here's where the exhaust velocity goes, and it's natural log of 22. I get a negative 0.49 for this first part. You can just type this all into your calculator, and then this 2.3 times the natural log of 22, if you do that correctly, you get 7.10939763. And then when we put those two together and do a little rounding, we get this maximum velocity to be about 6.6 kilometers per second. Not enough to get us to that stable orbit. So for this one, we're going to have to say no. It will not reach the stable orbit of 300 kilometers above the Earth. All right, get a new piece of paper here. We got 3 more examples to go through. All right. So here's the third one. What if I give you natural log of 2x minus 4 cubed equals 6? So now we're just going to practice some natural logarithmic equation solving. So I'm going to show you a couple different ways to do this one. First way, the kind of way the book shows you is, all right, well, let's do the cube root of both sides here. So I'm going to first use my logarithmic definition to rewrite this. So remember, it's base e, so it's really saying e to the 6th equals that 2x minus 4 that's cubed. And now here's where we do the cube root. To undo this power 3, I'm going to do cube root of both sides, and just to make it a little easier, I'm going to use power 1/3, so a rational exponent. So raising them both to the 1/3 power, or cube rooting both sides. I can use my power rules here and get this to be e squared. 6 times 1/3, remember, power of a power. I multiply exponents, and then the 3 times the 1/3, that gets me down to just 2x minus 4. Remember, e squared, that's just a decimaling number, and so this becomes just a 2-stepper. So e squared is 7.389056099, and that equals my 2x minus 4. And then I'm going to add 4 to both sides. So that gives me 11.389, and I'm just going to round this one now to 1 there, equals that 2x, and then divide away the 2, and I get 5.6945 approximately for my x. And I could put that back into the equation and double check to make sure that I get 6 when I do the natural log of that result. The other way that I was mentioning you could do is you could actually change this into 3 log of that 2x minus 4 equals 6. Divide away the 3 first, and then get natural log of the 2x minus 4 equaling 2, and then use the definition. Remember, natural log has base e, so that's saying e squared, e to the 2 equals that 2x minus 4, and then it works out just the same way. So either way, you could have gotten rid of the power 3 using logarithmic manipulations, or you could do cube root of both sides at the beginning. Your call on that one. All right, two more. Here's the fourth one here. So we're given 4e to the 3x plus a 1.2 equals 14, and asked to solve this equation. So we're going to end up using natural logs when we get to that point, but first I want to do my normal reverse PEMDAS and get rid of this 1.2. So I'm going to subtract 1.2 from both sides. I get 4e to the 3x equals a 12.8. Then I'm going to divide away the 4. I'm going to get e to the 3x then equals 3.2. And then I'm going to do the natural log of both sides. So when I do the natural log on this left side, I can make it 3x natural log of e, and then that equals the natural log of 3.2. So what I do to one side, I have to do to the other. So I'm doing natural logs to both sides. Now remember, when I do a logarithm, when the base matches this number, so the natural log of e, that's going to equal 1. So that's just this work. So I could have that e down there, and it is an e there. So e to the what would make an e, and the answer is 1. So basically, that natural log of e, that turns to 1. And so then we get 3x equaling the value of the natural log of 3.2, which is 1.16315081, and then divide away the 3, and that gives me x to be about 0.3877. And then if you wanted to, very easy to go back and just plug that in for x in the original equation and see if it actually works out. Now with some rounding, it won't be exactly 14 when you do it on your calculator, but it'll be really close. All right, one more of these. And this last one here is going to go back to that PERT, the continuously compounded interest formula. So they're telling us A equals P E R T for the exponent. And so we're saying, all right, we're going to have our principal be $200, and we're going to be told in how many years it's worth $254.25, and then it was 6% interest that we were making. So they're giving us all but one of the variables here. So I'm going to put in the numbers. This is the amount we had after t number of years. So that's going to be the 254.25 in for that A value. The principal, the original investment, was $200. And then E, and now the rate, the percentage as a decimal would be 0.06. And the T, that's our only variable left. We've got a letter here, but remember, E is just a number. So I'm going to divide away the 200 first, and that gives me 1.27125, and then that equals e to the 0.06t. And now I'll do the natural log on both sides. So if I do the natural log of this, this is just going to be a decimally number, 1.27125, and then I'm going to bring down my exponent, 0.06t, natural log of e. Again, that natural log of e is just going to equal 1, so it kind of disappears. The natural log of this 1.27125 number gives me this up just a little bit more. 2, 4, and a bunch of zeros, 4 zeros, and then a 6684. And that equals the 0.06t, and then divide away that 0.06, and that gives me t to be about 4 years. Really close. So after 4 years, you made yourself $54.25 in interest. All right, that's the lesson for today. Good luck. It's on pages 464 to 5 and number 2 through 40 evens. And we'll start getting ready for the test next week. Good luck and have a nice weekend.